Hello everybody, how are you doing? Today we continue our work with system of linear equations. The system of linear equations, and I want you to learn one new concept, and it is so-called inverse matrix. So let's start. I want to remind you that we have so-called matrix form of the denotation of linear equations. So ax equal b. I use the capital letters, which very often used for denotation of matrices. A here matrix of coefficients. X, it is unknown variable matrix. Matrix with unknown variables here, x's, and b, so-called free factor here, b matrix. So this is unknown variables here, and b matrix is it consists of some numbers or some expression of functions maybe. You know the so-called Cramer's rule, which enables us to calculate roots of the system of equations. But here I want to dwell your head on one thing. If you remember, when we use there's an equation ax equal b. Here ax and b are numbers, they are not matrices here. It's very easy to calculate root of this equation is by division by factor x. So a factor which besides to the x. So x equal b over a. It arises here the strong temptation to use the same approach, to divide both sides of the system of equations in matrix form by matrix A. But I can say that the direct division by matrices, it's kind of band operations, so it's not a quite right way. But the idea, the concept is good enough here. For this situation, for division by matrices, there is a special approach, multiplication by inverse matrix. And if it is about matrices, multiplication by an inverse matrix, it's kind of generic of the division by matrices. What do I mean? So there is so-called concept of the inverse matrix, and for matrix A, if matrix A, if the matrix A is square matrix, there is a matrix A raised to power minus 1, which is an inverse matrix. So that A minus 1 times A equal identity matrix. Identity matrix, it's kind of a unit matrix which consists of non-zero elements along this main diagonal, and all of them are 1, and all diagonal elements or entries, all of them are zeros. For example, here you have 4x4 matrix, 4x4 identity matrix, for example. And you remember, if you watched the video types of matrices, I have here extra zeros. I'm sorry, here we have some extra zeros here. So these identity metrics work like a 1 in numbers, in order of numbers. So if you multiply a matrix by 1, identity matrix, it gives the same as multiplication identity matrix by a, and it gives a matrix. So it works like 1, like unit for numbers. And this operation is a substitution of the division by matrices. So the main idea here, I use one more again, new ink, black ink. I want to get back to the black ink. So if you multiply both sides of the system of equations by inverse matrix A, it is possible for mathematics. You know, if you multiply one side by something, you can multiply by the same stuff, the right side of matrix. And this operation leads us to the identity matrix times x, and it is still x, and it is equal to the inverse matrix times b on the right side. So if you know what is the main idea of the bottom line of all this stuff, if you know these if you are able to define the inverse matrix, it is very easy to calculate roots of the system of equations. The only one operation you have to complete is to multiply the right side of the given system of equations by inverse matrix. And this result, this multiplication, I use one more again here, other one ink. This multiplication gives roots of the system of linear equations. Inverse matrix. So the bottom line here. So if you have system of linear equations, a times x equal b, next step, you have to calculate inverse matrix and inverse matrix, multiply both sides of the system of linear equations times b, and it gives you identity matrix times x equal inverse matrix times b. You remember that identity matrix times x gives x equal a minus 1b. So this is the roots of the system of linear equations. Okay. And now we have just know how to calculate these inverse matrix. The first one thing here. So we have to calculate how we can calculate these inverse matrix. Before we'll go to the calculation, I have to give you some definition. Firstly, I want to give you an idea of minor of the element aij. So, for example, A is a given matrix. Given square matrix. Put here all elements here. So it is a square matrix. I drop the some layers here. So this matrix n by n square matrix. A minor ij. Okay, I put here, for example, for this given matrix, in the body of this matrix, ij element here, for example. Minor ij is a determinant of the submatrix A, which obtained by removing the I row and j column from the matrix A. The determinant of the submatrix of A that obtained by removing the I row and j column from the matrix A. For example, an example here. For example, you have matrix A is a given matrix. For example, 1, 2, 3, 5, 6, 7, 8, 4, 5, for example. And I want to calculate 2, 3 minor. Minor is unknown here. How can I calculate? According to this definition, I have to pick out the element 2, 3. What does it mean? It is the second column and the third row. So this second column and third row, this is the element M23, A23 here. So since that I have to remove from the matrix A the second row and the third column, and here I obtain the new matrix. I define it like sub A equal 1, 2, the second I have to remove, and 8, 4, and calculate determinant of this matrix. So M23 equal determinant of the 1, 2, 8, 4 and it is 1 times 4 minus 2 times 8, and we have 4 minus 16, and it is minus 12. So this number is a minor to 3. Okay. Calculation. So we have minor, and also one concept is cofactor, so-called cofactor. For element Aij of the matrix matrix A. We denote like it's like A capital Ij is minus 1 raised to power I plus j times minor Ij. Cofactor. So this is the new definition here, cofactor, and this formula for cofactor. Okay. Now we are ready to make an example here. Example 1. Next one example here. You have a matrix A equal 1, 2, 3, 4, and I want to define all cofactors. No. Okay. So A11, we have A12, A21, and A22. We have just 4 cofactors here, and let's calculate them. Okay. For example, A11 equal minus 1 raised to power I plus j, it is 1 plus 1 times minor 1, 1. We know about minors, and we can calculate minor 1, 1 as a determinant of the what? To calculate this one thing, I have to find out firstly A11 element, it is 1, and reduce our given matrix by column 1 and row 1, and it is 4. Determinant of the matrix 4, you know the determinant of the 1 by 1 matrix gives the element of the matrix, so it is 4. Since that, A11 equal minus 1 raised to power 2 times 4, and it is 4. So we know now A11. A12 minus 1 raised to power A1 plus 2 times 1, 2, it is 2. We have to reduce matrix by first row and the second column, and it is 3 just. Minus 1 raised to power 3 times 3, and it is minus 3. So we can notice here that this cofactor is kind of the same element of the matrix A, but it changes its sign. So this is the first one factor in this given formula. It is the factor which changes the sign of the cofactor. And a22, it is minus 1 raised to power 2 plus 2 times 1, and a21 minus 1 raised to power 2 plus 1 times 1, not 1, but a21 it is 3, so times 2, and it gives minus 2. Okay, next one example. Calculation. Example. So matrix A is 1, 2, 3, 4, 5, 6, 7, 8, 9. And I want to calculate cofactor, for example, A21 and A31. Let's calculate firstly A21. So minus 1 raised to power 2 plus 1 times minor 2, 1. So you can see here that these indexes, they are always repeated. They are here and here. A21 element, I want to take the red ink here. Second row, first column. So this is this matrix element. I have to reduce our given matrix by the first one, by the first row column and the second row, and it gives to me minus 1 raised to power 2 plus 1 times the beyond part of the matrix, it is 2, 3, 8, 9. Minus 1 raised to power 3, it is minus 1, minus, we have here 2 times 9, minus 3 times 8. Since that we have minus 18, 3 times 8, 24, and we have minus 6, and it is just 6, so it's a new number. And now the last one thing here, A31 equal so the third, I use here green ink, 3, 1. So the third row, the first column, this element, these and these lines I have to cut out. So I have here minus 1 raised to power 3 plus 1 times 2, 3, 5, 8, and we have minus 2 raised to power 4, it is just 1, 1 times 2 times 6, 12, minus 3 times 5, 2 by 3. Okay, it's better, I think, to do step by step, if you don't mind. 2 times 6 minus 3 times 5, and we have 12 minus 15, it is minus 3. So we have here minus 3. Okay, Now we are ready to make our we are ready for a new formula for inverse matrix. A is the given matrix, the given square matrix. Inverse matrix can be calculated according to this formula: 1 over determinant of the matrix A times matrix which consists of the cofactors of the matrix but this matrix should be transposed before the use it as inverse matrix. This is the formula for the calculation of the inverse matrix. By the way, you can notice that if determinant A equals 0, it is impossible to calculate the inverse matrix, or we can say that there is no inverse matrix to the given matrix. And I can give here one more condition: if determinant A equal 0, we can say that there is no inverse matrix. If you remember, when we calculated roots of the system of linear equations, we said that we stated that if determinant of the matrix, which consists of the coefficients of the system of linear equations, equals 0, we say that this matrix is a regular matrix and there is no root. So here we have the same kind of condition. If it is impossible to calculate inverse matrix to the matrix of the coefficients, we can say that there is no roots and there is no determinants, there is no inverse matrix here.